That's why it'll be there.
Oh, fine. Yeah.
Atomic notation.
Yes.
So, atomic number, we have assigned the letter Z to. Why?
Z.
Because all the other letters were taken. I have no idea. They just decided Z was a good number to pick, so they picked Z. Okay? Mass number. They picked A to represent that. Why? A to Z. Who knows? Okay? Does it matter? No. What you need to know is what the atomic number is and what the mass number is. Okay? So what are those? Well, the atomic number, based on our notation down below, or even all the sentence structure, is the number of protons in our atom. Okay, so as soon as I find the number of protons, that will dictate what atom I'm looking at. Okay, that will actually tell me the symbol. Okay. The mass number is now going to give me information about what?
Number of protons, neutrons, and neutrons.
Mass number, the first word is? Mass. So the mass number is going to give me information about the mass. What particles, which of our 3 subatomic particles had mass? The protons and the neutrons. So if I want to figure out the mass number, what I'm going to do is add up the protons and the neutrons. Okay? That's where it's coming from. I then have that raw data. It's now a question of where do I organize it? Because I've got the atomic number, that's the number of protons. I now have a symbol because the atomic number tells me that or leads me to a key for that. And then I have the mass number. I could just list those all out as a string of information, or we come up with a standardized set of information on where to organize that data. And that is now what the textbook is calling, in my opinion, incorrectly, atomic notation. It is better referenced as nuclear notation. Why? What makes up an atom? Protons, neutrons, electrons. Atom is made up of all 3. When you look at that notation, where does it tell you about the electrons? It doesn't. Okay? That is because this notation was specifically designed for the intent of studying the nucleus. Who would care about the nucleus?
Chemists.
Most chemists actually don't worry about it. Give you a little descriptive picture here. It's not a tree.
Oh, nuclear physicist.
Nuclear bombs, okay, which use nuclear radiation, okay, which is all about the nucleus. So a nuclear physicist or chemist, depending on what you want to label it, will want to look at this information because they're concerned about the stability of the nucleus. The biggest part on the stability of the nucleus is the ratio of the neutrons to the protons. Okay? That ratio dictates radiation. So the very first thing that they want to see would be what's in the nucleus, the number of protons and the neutrons. So the first thing that they encounter in their notation will be the mass number. Because in English, we read left to right, or left to right, and top to bottom. So in the upper left-hand corner, the very first thing we encounter is the mass number, most relevant to a nuclear physicist. Okay? That's why they placed the mass number there. I saw at least one sideways glance that was presumably aimed at something other than other people in the classroom, and we'll get to that in a second. We then move to the atomic number. Why do we need the atomic number? So the neutrons could be different, yeah. So if I wrote out, let's say, 13C, I didn't specify the atomic number in that symbol, did I? And yet, what is the atomic number?
Wherever C is.
Wherever C is,
6.
6. Okay? Remember, the atomic number tells us what symbol to use. If I have the symbol, guess what? Putting the atomic number is now redundant. Okay? I have that information readily available to me. Because as a chemist, I always have handy a periodic table. Right? Regardless, depending on who you're looking at, sometimes they'll include that extra 6 to specify in a redundant fashion the number of protons. Right? And we have our notation. Questions about that? Okay. I made this big jump saying that this really only comes down to nuclear physicists, and we really only care there. Okay? And the question from that, and of course it's not going to work in the video if you're watching at home, but for those of you watching here, let's take a look at our periodic table. So according to our notation, what should we find above our symbol? The mass number. And not only above it, it should be to the left. So let's take a look at beryllium, and I'm now looking at it backwards, so I could be wrong here. So beryllium, Be, we have a number not in the upper left. There's nothing there. Okay, well, that's kind of weird. We do have something up above it. What is that number that's up above it? So 4, the atomic number. But the atomic number, according to our nuclear notation, shows up where? Below it and to the left. Periodic table doesn't show that. Okay? Where is the mass for beryllium found? Underneath it. So everything about this nuclear notation is not reflected on the periodic table. Why?
Is that intended to be standalone?
It's coming to our formats. That format is designed for who?
The rest of the world?
Nuclear, I'm attempting to point over there and still hold on to the sign.
Nuclear physicists.
Nuclear physicists. What is the big table for?
Chemists.
Everybody else in the world. Everybody else in the world is going to care about something else. What is that something else? Our first element is hydrogen. Our second element is third element. Fourth, beryllium. If we take a look at the atomic number for hydrogen, it is 1. Helium.
2.
Lithium.
3.
Beryllium.
4. Oh, it is.
Atomic mass. Hydrogen.
1.0.
1.00. We'll deal with the number later, but let's just say 1 for the moment. Helium. 4. Okay. Lithium. 6.9. Really, we should be rounding that to 7. Okay. Beryllium. 9. So yes, both of them are going up in sequence. Okay. But only one of those two goes in a direct numbered numerical system. It's almost like someone said, I want to organize this in the cleanest fashion possible, and I'm going to organize it according to the whole number 1, 2, 3, 4. Because guess what we did? We did exactly that. We decided to organize the periodic table according to atomic number, because the atomic number moves transitionally or numerically easily. The atomic mass, or the mass number, okay, which are technically different things, okay, do not move as easily in sequence. They will jump depending on the amount of neutrons also added in there. So it's not as clear a pattern. So we stick with the atomic number on our periodic table. Physicists don't care about the atomic number. They're concerned about the mass of the nucleus because that's what degrades and potentially kills them. That's why they want to see that information first. So depending on our audience, we will change how we present data. That's the intent behind our atomic notation as the textbook refers to it. Realize that the only time you will be using that formation or that notation is when you are looking at atomic notation. Right? So if I ask a question, what is the mass number, based off of a symbol that I'm showing, I'm expecting you to use atomic number. If I don't give you the atomic notation, you're pulling it off the periodic table. The information is located in different spots. Okay? We already addressed one of the massive issues with this periodic table in the last class. What was that major issue?
It doesn't have the name.
There's no key.
there's no key telling us red, blue, black, white. Okay? So when this gets mounted, I will also then be going through and printing on sheets of paper, hopefully large enough, that everybody can see the key of what red means, what blue means, what black means, what white means. The other part of it is it doesn't label where that information is found. Okay? That the atomic number is the number on top. The atomic or the mass number is the one on the bottom. So I will build a key for this periodic table so that you have reference to that. Okay? Because if we were in the lecture hall above us, guess what it has? A key. Right? So we need to make sure that you guys have the same tools that they do. Make sense? Okay. And if for any reason it does not show up in a timely fashion for the exam, feel free to yell at me. I'll write it up on the board. Okay? So, and I found out that we had an issue here. You ever had those problems where you start to save things in one file format and then you switch file formats? And it decides to edit everything? If you haven't had that experience, you're lucky. Right? Because it is exceedingly irritating. Our atomic number, silicon, I think we had this, and our mass number, 29. Okay? So for whatever reason, when I opened it up or changed it, it decided to slide stuff around. Okay? So let's erase some of that. So we have our example, 2914 Si. The element is silicon. How do we know it's silicon? The symbol Si. Okay? Because you went through that elements to memorize list and you memorized silicon because silicon is in the first 4 rows. Right? We've all done that? We're all doing that?
Yes.
Okay. The atomic number is what?
14.
Okay. We're given the notation up here, so stick with the notation. You don't need to look at the periodic table now. Okay. We would look in the lower left-hand, that's an eraser. We look in the lower left-hand corner, and we know the atomic number is 14. What does the atomic number tell us? Tells us that we have 14 protons. What's our symbol for proton? P, upper right-hand corner, positive. All right, what is its mass number? It is 29. It's the number in the upper left-hand corner of our nuclear notation. What does the mass number tell us? This is the protons plus neutrons. Okay? So if I want to figure out the number of neutrons, what do I have to do?
Minus 14 from 29.
Subtract the atomic number from the mass number.
29 equals our number of protons, which we had up here, was 14, plus the number of neutrons. I can now solve for neutrons, whoops, by subtracting 14 from both sides. Neutrons equals 32.
What?
Just checking. 15. Make sense? Okay. Questions about that?
I have a question.
Yeah.
Sorry, I'm trying to put my phone away too. Okay, I noticed this in the other one too. Why is the mass number 29 when over here it's 28.08? Why
If
would
we
it be
take a look at the mass on the periodic table versus the mass in our atomic notation. So silicon here I said was 29. If we take a look at silicon up here, you're saying it is
28 because it's
28, and it's not 28. It's 28.0855. Why is that say 29, that say 28? Sean?
Because silicon is different isotopes, and it's the average of them.
Okay. The mass in red on our periodic table here, underneath each element, is not the mass number. The mass number is by definition the number of protons and neutrons. The mass on the periodic table is the average mass number for that element. Okay, which is kind of a weird statement, and I don't remember how soon we talk about that. okay, in the slides, but it will pop up.
It's in the book reading too.
Okay? It is in the book reading. Okay? Remember, protons define the element, so I can't change the number of protons. But what do neutrons do?
They change.
The neutrons can change. I can have more neutrons than protons. I could have less neutrons than protons. That's going to change the stability of the nucleus. That's the amount of glue I put in to hold the nucleus together. Okay, I can decide, hey, heck with it. I want tons of glue. I want to make sure it's super, super tight. So I'm going to dump 4 bottles onto those 2 marbles to keep them glued to each other. Okay? That is now going to elevate its mass. Okay? But you're probably not going to dump 4 bottles of glue to keep 2 marbles together. Okay? So if we then looked at the amount of glue that each of us used as an individual and averaged that, that's what gets reported on the periodic table. So it is not the mass number, it ends up being called the atomic mass. Because it's an actual mass value that applies to the elements or the atoms of that type. Okay? So we can change the number of neutrons and we change the mass of our individual atom. Okay? When we say we, who is we that is changing the number of neutrons? Existence. Existence is doing it. Okay? Whatever you want to call that existence, it's already there, it's already happened. Okay? You can call it science, you can call it physics, you can call it mathematics, something happened. We as humans are not saying, I want an extra neutron in there, so I'm going to put one in. Doesn't happen. Okay? But what we're looking at is the total population for that individual thing. Kind of, sort of?
So should we round up?
We'll deal with rounding when we actually have to deal with some pretty hardcore, improve our level of mathematics. Trying to keep mathematics out of it for as long as possible, believe it or not. Okay? So, here's our big summary, atomic structure and the periodic table. What we have up here for our table is something that you should be able to fill in. Okay? So, let's spend, what do we want to call, a minute? Fill in everything you can in it. Ideally, do it in your notes. Talk to the people around you. Okay? I would argue you should be able to answer everything in that except for the last column. The last column might be difficult. But everything else should be verbatim, easy, nailed, probably within a minute. Okay. Officially, we should be saying outside the nucleus. That's 3 words. I don't want to write 3 words, so I'm just going to say outside. Protons. Okay. Inside, I would now argue, is too vague because we can add an extra word. That's where we can add in nucleus. Or if the pen started working, there we go. Neutrons. What is the mass of an electron? Hey, I'm getting a lot of people telling me 1 over 1,873. How many of you are good with numbers? Thumbs up, you're good with numbers. Okay, 2 people, 50-50. So half the class is good with numbers, half the class isn't good with numbers. Right? Based on that information alone, I would say don't memorize that number. It's pretty useless. Okay? I want to go lose weight, so I'm going to shave my head. Did I lose weight?
Yes.
Yes. Was that the intent of me trying to lose weight?
Maybe not as much.
Probably not, because I probably wanted to lose more than the probably less than 1/10 of a pound that is my hair right now. Okay? The mass of an electron is tiny. Don't memorize it as that stupid fraction. Memorize it as 0. It doesn't contribute mass. Okay? Protons, 1. Neutrons, 1. Charge on an electron, -1. Charge on a neutron. What was that?
0.
Yep, that was me being mean. Pay attention to the question asked. Charge on a proton,
Positive one.
+1. Our symbol.
E.
Some hesitation there because you're like, symbol on what? Our electron, E-, proton,
P plus,
P plus, neutron,
and
and 0, you could get away with just N. Now to the meaning. We've said the meaning now for protons multiple times. That doesn't mean it clicked. What is the meaning of the proton? It contributes to positive charge, but that is not its highest calling of meaning. What happens if I change the protons? I change the element. What happens if I change the electrons? Does it change the element? No. What happens if I change the neutron? Does that change the element? No. Guess what the protons do? They define the element we're looking at. Right? Neutrons or electrons, which one do you want to look at?
Electrons.
Okay, electrons. What is the meaning of our electrons? What do they do? If I change the number of electrons, does that change the element?
no.
Good, because it would really suck to have a meaning that was the same as something else. Okay? So I want a different meaning there. What do the electrons change?
So it changes the charge.
The electrons are going to change the charge on a given element. Yes, protons contribute to that charge, but once I've defined the element, I can't change the protons. The only thing that's going to change the charge then would be the electrons. Okay. Neutrons? Yes, it contributes to stability, so that's what it's doing, but I want to know what its meaning is. It's going to define the isotope, or the mass. Okay, I would argue mass, because isotope is too big a word for me. Shh. Don't judge. Okay. That helps us then narrow down. So if I see something about charge, I know I need to be looking at the electrons. The electrons are going to dictate it. Do I still need the protons?
Yes.
Yes, because charge is the balance of electrons and protons. Okay, so protons have their fingers in all pies. Okay, but the only thing that is solely them is defining the element. Kind of make sense? Okay. So yes, this would be a quiz if I'd remembered to cut enough stupid little sheets of paper to pass around, and I don't want to collect your random loose leaf pieces of paper. Okay? So because of that, my fault, maybe I'll just move this quiz to later on. Okay? We could do it orally. I'm fine with that. Provide the name of a famous chemist or physicist that contributed to the understanding of atomic structure. It's not structure.
Really?
Too late. Oppenheimer's late. Atomic structure is going to be earlier than that. You blew it up. That's true. Thomson. What did Thomson do? Really defined our electrons. Okay. Who else? Rutherford, because
See what the guy did with the gold foil?
did the gold foil. So we've got a keyword tied to him. But what did that prove?
Prove the mass.
Proved a nucleus. Okay. Proved I had a super dense nucleus. Okay. What other scientists do I have? Curie. Okay. Radiation, which is a little bit of a long shot for understanding of our atomic structure, but it's kind of there.
Dalton.
Dalton, did he help us with atomic structure? No, so it doesn't quite work as well, but what did Dalton do?
Atomic theory.
His didn't really organize very well either because we didn't use that periodic table. Remember we had 5 rules that 5 laws of Dalton? The first 2 were wrong. The first 2 were all about atomic structure. What were the last 3 about? Building compounds. Okay? So arguably, again, not atomic structure, but he is looking at how we build compounds, what we can do with those atoms. What was another scientist's name that we hit? Millikan. What did Millikan do? The charge on an electron. Okay. Last scientist's name that could kind of float in there, I said don't stress about it for this class. What was that? Oh, Fletcher. Fletcher's tied to Millikan. So either of those names would work. Back to the charge of the electron.
Who's doing the oil test?
That was Fletcher and Millikan. Fletcher and Millikan are our oil test. Did we talk about neutrons yet? That was Chadwick. Okay. So those are our primary contributors to atomic structure. We could then take that atomic structure and do all sorts of crazy stuff to it, like blow it up. That's further on down the line. We still needed our atomic structure first. Okay. A topic to be discussed at any point from here forward in today's lecture. How would you be able to figure that out? You downloaded the slides. Oh, that sounds like a repeating pattern I'm asking for here. Okay. Maybe you should do that so that you don't have to draw all the stuff that's on the slides. An isotope was isolated with 88 protons and 138 neutrons. Provide the atomic notation for this element. Okay. The last one would then be, why might ask a question about this? Okay. So, you want a second to work on that? Yes, do it. What are you doing? That's cheating. You need Google to look something up?
No, I did that, but I'm looking up the name. I don't have my little sheet in front of me.
Oh,
I can't
fair
see
enough.
that far.
Fair enough. Download a periodic table app.
I mean, well, I printed one out.
Just saying.
Oh, that's a triple positive no.
What's that?
No kind of gas.
So that was fun. I forgot to hit pause on that, so it kind of ran it out. What's the question? I should be there Friday, probably in the 10 to 12-ish range, I think. Yeah, that is my hope. Yep. Yep. Okay, so what was the mass number?
Mass number is 226.
Fair answer to the question I asked without numbers. What is the mass number?
The protons.
Mass number of protons and neutrons combined.
Protons and neutrons, the atomic number.
88. Just the atomic.
No numbers.
Just the protons.
Protons. Okay. Where did I get SY from?
Whatever is on the periodic table.
SY is the symbol for that element. What dictates the element?
Proton.
The number of protons. So the first thing I need to identify in all of that information is my atomic number. The number of protons, which happens to be
88.
88. With that information, I can now go to the periodic table and I can find element 88, which happens to be radium, or Ra. Radium.
Let's do proton.
Okay. The mass number is the number of protons and neutrons.
Together.
So we add up 88 to 138, and someone said
226.
226?
226,
Yeah.
yes.
Okay. For those of you wondering why it takes me so long to do math, I'm not good at math. Okay. It's very slow. That's why I ask you for help. There's our atomic notation. Sweet. Okay. Why might ask a question about this? Madame Curie discovered the purification scheme for radium. Okay. Why is that important?
She killed a lot of people accidentally.
No.
Wow.
She really killed herself accidentally.
And then
Not.
all of the people who used radium in painting and in building and in a lot of stuff.
Yep.
Luminous watch hands.
Yep. Okay. Why do I care? Why do we care that she discovered radium? Lay the groundwork for other radioactive discoveries. We listed Curie as an important scientist getting at our atomic structure.
She made alpha particles.
She made alpha particles. Why do I care about alpha particles?
before alpha particles, Rutherford would never been able to
Alpha
discover the
particles
particles.
were what were used to fire at the gold foil for Rutherford to define the nucleus. We don't have alpha particles, we don't have radium, we don't have a nucleus. Okay? Or we don't know that a nucleus is there. That's a pretty important discovery. That's why I picked it. It also involves some math that I couldn't do in my head. Okay? Questions about that? Okay. Isotopes. So we said our protons define the element, and the neutrons define the isotope. Okay? Type of element is a horrible word to use there. Let's get rid of the type. Let's change it with a better word. What word should we use? What did neutrons define? The isotope, also known as our mass. Okay? So atoms of the same element can have different numbers of neutrons. Those different atoms are called isotopes. For instance, hydrogen, if we take a look at hydrogen off the periodic table, and we look at standard notation, we had hydrogen with an atomic number of 1. If we look at the number on the periodic table for our mass, what do you think the mass number is most likely to be? 1. Why?
It doesn't need a neutron to keep it balanced.
Okay, so there's a further step down on the why. Why am I saying the mass number is most likely to be 1?
Only needs one.
What is the atomic mass on the periodic table? 1.00795. More than likely, the mass of hydrogen will be 1. Okay? It matches what's on the table. So that would be our notation. Notice I have that notation written above, and I'm not calling it hydrogen, I'm calling it protium. Why would I call it protium?
Distinguish it from hydrogen?
What is the nucleus of a hydrogen atom made of? 1 proton. Why is it only 1 proton? Why do I not see a neutron there typically? Go for it.
Because there's nothing needing to keep it together. It's only 1 proton.
What was the role of the neutron? It's the glue to hold protons together. If there's only 1 proton, do I need glue? No. Okay. So hydrogen does not typically have neutrons. Can it? Yes. Right? So if we're looking at hydrogen with no neutron, we could call it hydrogen. That would be correct, but we could refer to the isotope name for hydrogen and call it protium. Why prot? Because there's only 1 proton. That's the only thing in the nucleus. What happens if we add a neutron? I want you to use a different word than atomic mass. Yes, it does technically go up, but I don't like atomic mass. What's a better word to use than the atomic mass going up? The mass number goes up. Okay, you might say, well, what's the difference, Mike? Aren't they the same thing? Technically, no. The periodic table gives you the atomic mass. Notice all those extra decimal places and all that annoying stuff to worry about? That's the atomic mass. It's for the entire element population. Okay? The mass number is by definition the number of protons and neutrons. They are similar, but not the same. Okay? So what happens when I add a neutron? Well, is it going to change the atomic number? No, because the atomic number is just the number of protons. So when we look at my symbol, I still have hydrogen. Man, I need a new pen. And my atomic number stays 1. But notice what happened to the mass number. It increased. Why would it increase? I added a particle that has mass. I added a neutron. So it goes up by 1 mass unit to 2.
Is this something that happens naturally, or is this something we did?
This happens naturally, and there are byproducts where we can make stuff like this, but it does happen naturally. Okay, or it exists naturally, we should say. Okay? We now have a different isotope because the mass is not the same. This is one of the reasons why I think it's rule 2 on Dalton's list is false, is because of isotopes. Because if I look at the mass of protium and the mass of deuterium, they have different masses, which means they have different properties. Okay? Which means not all of the same element have the same properties. That's why his rule is false, because of isotopes. Okay? What do I want to name this? Cheat, it's up there.
Deuterium.
Deuterium. Where's that coming from? Dew for deuce. Okay, also known as 2. Why would we call deuterium 2?
That's 2.
Because the mass number is 2. Okay. Turns out that we can also end up with hydrogen with 2 neutrons. Okay. So we need to come up with a new name. Being the creative scientists that we are, we had protium because it only had a proton. We had deuterium because it now has a mass number of 2. The next one has a mass number of 3. We could call it threeium. Well, that doesn't sound as cool, so we drop in tri for 3, and the tium because then it sounds cooler. We got a transformer now. And we have tritium. When you hear people, oh, tritium, blah, 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 it's hydrogen with 2 neutrons. Okay? So if I look at a sample of hydrogen, that sample of hydrogen will have protium, it will have deuterium, and it will also likely have tritium. Okay? What should I report for the atomic mass on the periodic table? The average of those. So if I average protium, what's its mass? 1. Okay, calculating an average, right? How do we do it? That says average. 1 plus 2 because deuterium has a mass of 2, right? Plus 3 because tritium has a mass of 3. And now what do I do? Over 3. Why 3?
Because there's 3 numbers.
There were 3 pieces. Okay. What mass do I get? 6 over 3 is 2. So according to our calculations here and what we've just discussed, what is the atomic mass on the periodic table supposed to be? 2. Is it 2?
No, because there's a lot more than just
Okay.
R.
What we're looking at on our periodic table, this calculation assumes an equal percentage of each of those 3 species. Okay. That's not true. 99% of all hydrogen is protium. Roughly 0.999999% is deuterium, and the last 0.000001% is tritium. If I factor that into my calculation, I then get the correct mass for hydrogen. Okay? So it's looking at population dynamics. We can't just say absolute averages, because the absolute averages make the assumption they're all equal. Okay? This brings in some mathematics that I'm not particularly a fan of, because it's mathematics in general, okay? But that's where it's coming from. Let's take a step back from the calculations on that. How many protons and neutrons does an atom of lead-206 have? That's going to be an interesting question. That's a different format. See what you can come up with. Talk to people around you. This question drops a lot of things on you that makes it a little bit more challenging. So we need to break it down based on the information we know. Okay? If we're looking for protons and neutrons, really what I'm looking for is some kind of atomic notation information. Okay? A lot of that information is stashed on the periodic table. How are my elements presented on the periodic table? As symbols or names? Symbols. Step 1, what do you need to do? It's going to be hard to figure out the atomic number if you don't know where to look. You need to know the symbol for lead. Step 1, did you memorize your symbol to name matching? If you didn't, you're SOL for the rest of the question. Okay? So that's why you need to memorize these things.
That's not in the first 4 rows.
That's true. I said the first 4 and then random ones after that.
And I think
Unfortunately.
82 is one of them.
And lead, being a super common element used, shows up a lot, is one that you are required to know. So, lead symbol is PB.
Peanut butter.
Like kind of the opposite of peanut butter is and never eat it. Right? But yes. Since I now know the symbol is PB, what can I do with the periodic table?
You can figure out the mass number.
I can come up with the atomic number first, and we'll come back to why I want the atomic number, not the mass number. Okay? Whoop. Why go to the atomic number?
Because you already gave us an atomic number of protons and neutrons.
We'll come back to that in a second. Why go to the atomic number? The atomic number is the amount of protons which is defined by the element. Once I know it's lead, I know the atomic number. Okay, once I know that PB. That is a guaranteed statement of fact. Even if I don't understand the rest of the notation, I know the atomic number because I have the periodic table and I remembered that the symbol is PB for lead. Okay? So, when I find it, where to go? This is where we have to have fun with the periodic table. You should be studying it and getting a general idea of where everything is located. I'm not expecting you to memorize it, but I am expecting you to be somewhat familiar with finding things on the periodic table. Okay? If you have some bulk classifications, you can whittle down and speed that transition or speed that process. So our atomic number for lead is
82.
82. Why is it not 207.2? The 207, I already lost it. There it went. 207.2 was our atomic mass. Okay, not the mass number, or not our atomic number. The atomic number is the big one up top. So 82. That tells me that I have
82 protons.
82 protons. Most of your tests, particularly this kind of question, would be a straight multiple choice because there's virtually no work to show. So on an exam, you wouldn't need to show all of this work, but this could help you through it. Because say some jerk didn't talk about this notation. Right? Did I tell you what lead 206 in that formation meant? No. Can you figure it out based off of what we've talked about? Well, we know lead is PB. I know there's 82 protons. Okay. What the hell is 206 then? That has to then be the mass of the neutrons plus the protons. Okay? Because there's no other information that would suggest otherwise. Okay? So through a process of elimination, I can reason my way through on stuff that I already know. The strength that I've already talked about. That's what you need to be doing on every exam question in this class and every exam question in any other class. Take advantage of what you know. Make sense? Okay, so with that, if I know 206 is my mass number, what was the mass number? Protons plus the neutrons. My protons happen to be 82. Protons was just 82. I can now solve for my number of neutrons by subtracting 82 from both sides. And I would get, that's 421. I now know the number of neutrons and I know the number of protons. I've solved the question. Let's take it one step further. Let's say you didn't know that notation at all, but you at least got the number of protons. Guaranteed one of the answers has 206 protons. Can lead have 206 protons? What you just found was a failure. What should you do with that failure?
Learn from it.
Learn from it. Cross it out. It's a wrong answer. Mark out wrong answers on the test. It's very valuable. Okay? Please do that. Questions on that? Okay, so let's open up the next can of worms, which is indeed there, our percents. Okay. This is technically in the PSS section of our book, I believe, on understanding percents. Most people seem to understand percents, at least ballpark, reasonably well, because if you get an exam and it says 90 on it out of 100, you go, yay, because that was a what percent? A 90%. What did that mean? You scored 90%. What is cent?
Short for 100.
It's short for 100. So your percents are always looking at out of a possible sample of 100. That's what that word means, percent. Right? We can use that information to help us interpret how we go through and evaluate things. Right? You will also potentially see through science that percents can also be labeled as by mass or by volume. Okay? What we're saying there is that when I look at that quantity, I'm saying the units of the quantities in mass would be a mass unit, like grams or pounds, okay? Ounces, those kind of mass units. If I say percent by volume, how am I calculating my percent? I'm using liters, pints, quarts. I'm using all of the units associated with volume. Okay? So let's take a look at an example here. I've got bronze, an alloy of copper and tin. Okay? If a sample of bronze contains 79.2 grams of copper and 10.8 grams of tin, what is the percent copper in the bronze? Okay? Ignore the second question. I'll make you guys do that one on your own. Okay? So what am I trying to solve for? The percent copper in the bronze. Okay? So quite likely one of our answer choices is 79.2. Why is that wrong? 79.2 refers to copper. Is that the percent of copper? No. Okay? So we have to recognize what we're solving for. To get the percent of copper, how do I solve?
79.2 over 90.
Let's avoid numbers. I know everybody wants to jump in and throw numbers. Numbers will be the bane of your existence. If you can avoid numbers and use symbols and notations, that will help you out better in the long run.
Total copper plus total tin.
It's one quantity, the one we're studying. We want the total of, why did you say copper?
Because that's what we're trying to figure out.
That's what I'm trying to figure out. It says percent copper, copper's on top. Over what?
Total copper plus total tin.
The total, we could say copper and tin. What else could we say?
Bronze.
Bronze.
Oh, yeah.
Right? It's the copper in that bronze sample. Right? So what is the total copper in that sample? And I always forget this.
79.
Times 100%. What was the total copper in the sample? 79.2. Technically grams. Okay. What was our total bronze? What is bronze?
Copper and tin.
According to the question, it's an alloy of copper and tin. So to figure out the mass of the bronze, what do I have to do? 79.2 grams plus 10.8 grams times 100. Thank you for reminding me on that. 79.2 divided by, I'm hearing a bunch of people say 90, times 100. We cross, multiply, divide, and we end up with 88.0%. Let's just pretend that wasn't there. Okay? Kind of, sort of.
So, like on a test, would we have to show like total copper over total bronze times 100?
So there's an interesting question. Where would a question like this potentially show up? Okay, yes, on a quiz. Let's think back to the exam content. Our exams are composed of two sections, multiple choice and show your work.
Show your work.
Why would it show up and show your work?
Because there's work to be done.
There's work. Okay. Admittedly, is there a lot of work? No. Right? But it is a show your work type question. You could expect to see this in a show your work section. How much of this is necessary for credit? Okay. Ideally, all of it. Okay. But the ideally is more for you than it is for me because you can now check your work. What I would be looking for to get full credit, I think I can get away with this.
79.2 over 90.
Yeah,
would really be that. I actually don't even want to see the 90 right away. I want to see the 79.2. Okay? So if we push this even further, the absolute minimum to get credit would be this. That's now full credit for the question. If you jump to 90, where'd you get 90 from? Yes, I know that is the addition of those two, but I don't know that you know that, which is dumb. But that's how it works. Okay? That gets full credit. Okay? Ideally, we also have the 79.2 over 90. You've added a little bit of extra work there that helps you out, because maybe you go through and you entered it into the calculator wrong, and because you didn't write this step, what you did was 79.2 plus 10.8 and then said divide by 79.2. You did all that work in the calculator, your answer comes out wrong, you get the answer wrong, but your work is right. By adding that extra step, you can sometimes see it and miss that calculator mistake. Okay? So a lot of what we'll talk about is just ways to simplify calculator mistakes or avoid them as best as possible. You don't want those tips, so that's fine. Don't listen to me. Okay? But by corollary, I then won't listen to you when you make those calculator mistakes. Make sense? Okay. And then also ideally, yeah, there it goes. We would also have the text written out for what's happening there. Okay. That is my ideal scenario. That's what I would write into my key. What I would also write into the key would probably be 1 point, 1 point, and the answer is almost always worth 2 points. Okay, worth more, slightly more than the work. So if you just got the multiple choice answer, you get half credit. You show me the rest of the work, you'd get full credit. We good? So erase it all. How much tin is in 100 grams of bronze? That's on you now. I'll give you 3 to 5 minutes. Okay. Yep, we're back to recording. Come on. Oh, man, all the way back.
Right as you start recording.
How much tin is in 100 grams of bronze? Okay. One of the really important aspects that we need to cover with all questions is what are the units that we're looking for. A number is meaningless if I don't know what it's in reference to. So I need those units. So when we take a look here in that question, does it tell you the units? It says grams of bronze. Does it tell you what units we want for tin? No. That's because it's a crap question. Okay? You will find crap questions all over the place. Okay? Everywhere you go, you'll find them. Because the person writing the question knows the answer that they want. They don't see the things that are missing from the question. Okay? I try my best to very carefully analyze every single question that I ask to prevent this type of ambiguity. If it shows up on an exam, call me out on it. Okay? If you don't call me out on it, it ends up later coming back where I'll then have to remove it from the exam. If you got that question right, that doesn't help you anymore. Okay? So you should call me out on it so we can clarify it. So in that clarification, no! I intentionally went slowly on it so I could get all those letters back. If we clarify how many grams of tin is in our 100 grams of bronze. Now it's clear what we're searching for. We're searching for the grams of tin, right? Okay, so how could we go through and solve this? What's that? Okay. So what you're saying is that I could say percent of tin is, what was it? I already forgot. 10.8. Oof. That's what happens when you don't look at where you're writing. 10.8 grams of tin over that 90. That's a lowercase n. Okay. Over 90. Where'd you get the 90 from? Okay. We remembered that from our alloy of bronze from the previous question. Officially, you should show that work. Okay. Then what you've done is technically said times 100%, and you've now got the percent tin. Right? Okay. If I want to figure out grams of tin in 100 grams of bronze, what we can do is track our units here and stop looking at our percent tin and say, well, I know I have 10.8 grams of tin in 90 grams of an alloy. How many grams of an alloy do I have? What happens to the unit of grams of alloy? One's in the numerator, one's in the denominator. They cancel. What units would I be left with?
Grams of tin.
Grams of tin. What was the answer I wanted? Grams of tin. Hallelujah. There's my answer. Okay. There are other approaches to it, all getting at the same intent or the same directionality. It's just coming from it from a slightly different angle. If you want to see those other ones, talk to me after class because we are done.
So say,